Hi, welcome back. So we were at the Nusselt number, trying to find out the Nusselt number. So we did arrive at this. We were somewhere here, right? We got an expression for the Nusselt number, right? We did some math and tried to find out the Nusselt number. Now let's see if we can expand on this a little more. Okay, if we can do this a little more. So therefore, now again, the Nusselt number, therefore, I can write as minus L, okay, del y. Now, what did we define theta earlier on, right? We did define theta, see? We defined theta as t minus t infinity by t w, t wall x minus t, right? So, what we have here in this expression, if you see, is just that. Okay, so it is nothing but theta at the wall, right? If that is true, so then I can write this as minus this del theta at the wall eta del eta del y, right? So this is equal to minus L, right? This is theta w, this is the derivative of the temperature difference, right. So, you are taking a derivative with respect to eta, okay, and del eta del y is nothing but under root of R e by L delta bar value of zeta. Okay. So, again these two L's will sort of cancel out. Okay. So, therefore, we can write that the Nusselt number by the Reynolds number, okay, is equal to wall by zeta, right. That is a nice expression to use. So, we will have, right. So, the of course, then combine this. So, that we are going to call this as 12. Okay. So, I am going to call this as 12. Okay. And of course, we will have standard boundary conditions. So, of course, T wall is constant, okay, which means eta is 0, okay, then Q wall is constant, okay, zeta by constant. Okay. So, now if we, so we've kind of, we're going to just sort of take a, step back and look at this a little bit. Okay. Now, what we'll do is we'll compare equations 4 and 11. Okay. Now, 4 and 11, it's very interesting. Okay. Now that we've got an idea about Nusselt number and all that. Okay. So, we'll see now if we understand some things out of it, and if the equations are telling us, it's giving us some more equations. Okay. So, what we will do is look at equations 4 and 11. So, what was equation 11? Let's go back and look. So, basically this is equation 11. Okay. If you look at this value equation, this is 11, and 4, this is equation 4. This is equation 4, this has been derived earlier, isn't it? This has been derived earlier. So, now, these are the two equations. Okay. Now, okay. Now, for a flat plate, for example, okay, for a flat plate. Okay. Alpha 3 is 0, alpha 2 is 0. Okay, right? Now, then you let alpha 4 equal to alpha 3 is 0 and this Prandtl number to be equal to 1, right? Then what happens to the two equations? To what happens to equations 4 and 11? If I do this, then what I have, then equation 4 basically becomes this plus alpha 1 f of f double dash is equal to 0. That is 1, and the equation 11, right, it becomes theta plus alpha 1 f of theta dash, okay, is equal to 0, okay, and this is this way. Okay. Okay. Now, let us look at these two equations. So, this is essentially, this is from equation 4 and this is from equation 11. Is that right? So, now see equation 2, right, is exactly now. Okay, now let us sort of see what is the difference, between these two equations. Now, for a second, for example, just forget that this f and theta and these things mean anything. Just think of them as two, just symbols, and we have written some differential equation here. So, just see what is the difference between 1 and 2 that we have written here. If you want to sort of gauge it, look at this a little more attentively. From what I can see, that these two equations, equation 2 can be exactly equal to equation 1 if theta is equal to f dash. What I see is that we have f triple dash and I have theta double dash. I have alpha 1 f, and I have f double dash, right, and I have theta dash. So, if theta is equal to f dash, so think about that. So, theta double dash will be f triple dash, right, and so this would mean that theta double dash will be f triple dash, okay, and theta dash would be f double dash. In that case, if this case 2 will be exactly same as 1. Okay? Exactly same as 1. Okay? Now, what does that even mean? Does that mean anything? Okay, what is the implication of that? So, let us see. Okay, let us see. So, we are basically saying that theta and f dash, of course, they have a physical meaning. I mean, we know that, right? Now, we saw that if we sort of played around with these values of alpha 1, alpha 2, alpha 3, alpha 4 and the Prandtl number, we get something like this, and from our studying of these two equations 1 and 2, we get that these two can be exactly same with each other if theta is equal to f dash, right. So, what does that even mean? Does it even mean anything, right? What is the implication of that? Now, we know, right, we know that, okay, let us use this space here now, okay, fine. So, f dash is nothing but u by v, right. In this case, this is equal to theta, right. So, of course, if I were to, it's very important to sometimes, we write down expressions in math, but they start making to mean something only when you sort of, read them aloud in full sentences. So, let us sort of write that down. What does this even mean? This thing that we just wrote here, that non-dimensionalized, right, this is not, theta is nothing but non-dimensionalized temperature, right, is equivalent, okay, to the non-dimensionalized velocity, right. Non-dimensionalized velocity or the first derivative of the similarity stream function f. Right? That is what this thing means. Let me write that down. So, what this essentially means, right. So, from all of this, what I can write is non-dimensionalized temperature, okay, temperature difference, temperature rise is equal to, equivalent to, is equal to number 1, or let us just say A, okay, is equal to non-dimensionalized velocity right, or basically or, you know, the first derivative of the first derivative of f, you know, which is the non-dimensionalized of the of the similarity stream function, okay, stream function based on the similar variable. So, first derivative of the stream function f, which is a function of the similarity variable eta, right. F is a function of eta. So, what I am doing here is, you know, this is very important for you to do sometimes. So, when you look at something like this, right, just sort of jot down as to what inferences you get. So, you could write, you know, inference. For example, I would write what is the implication, whatever, does not matter. So, what is the inference? That the non-dimensionalized temperature, right, is equivalent to non-dimensionalized velocity, or the first derivative of the you know, the stream function, which is based on the similarity variable, right. So, now wall shear stress, okay, wall shear stress right, and okay. So, now wall is this, right. So, therefore, y is 0. So, I am going to write again. So, therefore, I am going to write tau wall as nu del u del eta at eta is equal to 0 into del eta del y at y is equal to 0, right. So, I am just breaking down this the derivative here with respect to y when I write the wall shear stress in the similarity variable. So, I am just writing. So, essentially I mean what I am doing here is writing it as del u del eta into del eta del y, that is all, right. So, that, right. So, therefore, in this case eta is 0, in this case y is 0. Okay. So, if I do that, so now for example, okay, now u, right. So, f dash is basically equal to u by v, which we just wrote here. This is something that we know, right. So, therefore, del u del eta, right. See how interesting this is nothing but f of double dash, right. So, del f dash del eta, so that is del v f double dash, right. And del eta del y, well, that's equal to v by 2 nu x, right. That's basically the math, the way we define that, right. So, therefore, tau w, okay, is equal to nu del u del eta at eta is equal to 0. Okay. So, del u, which is say del u del eta, right, at eta is equal to 0, where f double dash is yeah. So, let me write that down. Okay, let me write that down. So, this, and it is v f double dash, right, eta is equal to 0, okay, into delta eta delta y at y is equal to 0 into v 2 nu x, right, 2 nu x. So, then so basically that. So, then therefore, or, okay, at the wall is equal to nu, okay. So, f double dash at eta is equal to 0 is, what is f double dash, right, f double dash at the wall. So, okay, I think you can just go back and look up that when we sort of did this, but or sort of think about what it will be. Okay, I'm just going to say that this is going to be 1. So, cross check. Okay, just cross check that. Check that for yourself. So, I'm going to write v. Okay, and v, and then I write this v 2 nu x. Okay, so let's just say, okay, so I will just say this is f double dash at the wall. Let me just write it that way. Okay, so what happens to, so think about how this f double dash eta is 0 or f double dash at the wall will behave. Okay. Okay. So, therefore, shear stress at the wall for me, if I were to write this down. So, this is shear stress at the wall. Okay. So, this is shear stress at the wall, right. Is that right? So, then of course, then our interest is of course in the coefficient of friction. So, then we know that this is equal to half rho v square, okay, into say, so yes, so shear stress. So, this is well, usually I hope you remember that coefficient of friction, right. So, that's basically force, right, by dynamic pressure into area. So, since we are writing the stress, so that force by area is going to this. Okay, so, we do not have that area term in case you are getting confused. So, then I will write this at 2 by rho v square, and I will put in the expression for the tau wall that we just wrote out, right. If I do that, so then I get nu v by 2 nu x into f double dash this, right. If this is true, then this is equal to under root of 2, okay, by v. You can do the math a little bit. So, this v at the numerator cancels one v of this v square, okay, and then I've got a root v here, okay. So, I bring that, so then this I kind of cancel one root, so then I get v here, okay. That, and then you have nu, and then you have x, right, that is okay. And then again I will write this as f double dash at the wall, okay. So, then this is giving you further hints as to what, if I could write it further, okay. So, okay, did we miss something here? Okay, sorry about that. So, we've got this, we've got what we missed here is that we got a nu and we've got a rho, right, the mu and the rho. So, that will be a mu like that. So, what we will get here is therefore root of 2, right, nu by V x f double dash w, right. So, now it makes it clear. So, what do we get now? So, therefore, this is equal to 2 by R e. Hopefully, that is not too difficult to see here. So, therefore, this is nothing but our coefficient of skin friction, right. So, this is nothing but our coefficient of friction. So, if you remember the computer code that we wrote, right. So, we were getting outputs, right, for f dash, for f double dash. So, and then we were wondering what are we going to do with that, okay. One is, of course, if you can see here that if I get an output for the f dash, right, f dash. So, then I should be able to plot u by v, right. So, I should be able to do that. So, that's what the solution is going to do. Okay, so, you can plot out the velocity profiles at different x locations depending on what surface you are looking at. That's what we mean by a solution, right. So, and then if you continue further, so if I should get a plot of f w, right, I mean I should get an output of f double dash at the wall. So, then I can use that to calculate the coefficient of friction, right. So, that's that. Now, let us dwell a little further sort of on this, okay, and see what we will get, okay. Let's do this a little further. So, now since we are on this, okay, now we will write h, we will define h as, right, this, okay. So, if I do that, then what I get is, I will write this as 1 by T w this, okay, into that at y is 0, okay. So, I can write this as right. So, I am going to write this at T w, okay, I am going to write this as T infinity minus T w and T w minus T infinity minus k del theta del y, y is equal to 0, So, again we will do, so therefore, basically we get h is equal to, so this. So then, so therefore, or say H is equal to K delta theta delta y at y is equal to 0, which again I can write as K delta theta delta eta, eta is equal to 0 into delta eta delta y, y is equal to 0, right. So, which is again equal to K theta dash, okay, at the wall, because eta is 0, right, and this again we know. So, therefore, that is V 2 nu x, okay, 2 nu x, okay, or H is equal to K theta dash this, okay, into R e by 2, okay, or we can also write or H by K under root R e is equal to theta dash at the wall by 2. Okay, but that's something we know, right? That's something we've been, that's what we were sort of talking about, isn't it? Okay, now again, H by K, right, is equal to Nusselt number. Okay, so therefore, Nusselt number is equal to or say Nusselt, right. So, now H by K here in this expression is Nusselt number. So, therefore, I can write, so if I replace that by under root of R e is equal to theta dash at the wall by root of 2, right. This is again equal to F wall double dash, because theta wall, theta dash of the wall is equal to F double dash by root 2, right, which again, if you go back and look at the coefficient of friction, which we wrote in terms of F dash. So, from there if I write, so then that is equal to, so F double dash by root 2, right, by root 2 should be equal to okay. So, then wait a sec. So yeah, so F double dash by root 2. So, what we get is C f, okay, under root of R e by 2, right. So, right, or Nusselt number, okay, by R e is equal to half this thing. Now, this is a quite a revelation to us, isn't it, right. So, skin friction coefficient, right. So, therefore, the skin friction coefficient and Nusselt number are connected through the Reynolds number. That's quite interesting, isn't it. So, in order to, in other words, in order to calculate the heat transfer, right, at the wall, right, knowledge of the skin friction coefficient and Reynolds number are sufficient. You don't need to do anything else. You don't need to kind of go and solve the energy equation separately. Just this information is sufficient, and of course, it's kind of easier to evaluate CF and coefficient of friction and the Reynolds number. Now, this is a Reynolds analogy, but please remember that we were able to get all of this only when for Prandtl number 1. Okay. So, let me sort of write that down. So, what this is basically telling us, is that skin friction coefficient, okay, and the Nusselt number right, are connected through the Reynolds number. Okay. So, right, so I am now going to write the rest of it. So, basically what you can see here is that in order to calculate the Nusselt number, all you need to do is calculate CF and RE. You should be able to get that, which is easier to do, right. So, this whole thing that the skin friction coefficient and the Nusselt number are actually connected through the Reynolds number, this is actually the Reynolds analogy. Okay. So, this is basically for Prandtl number 1, right. So, this is when we were comparing equations 4 and 11. So, that is how we came up with. Also, I mean, so I will just sort of, before I close, just write up this small expressions, and then we will close. Okay. So, the Stanton number is essentially dimensionless. The Stanton number, okay, dimensionless heat transfer coefficient. So, that is dimensionless heat transfer coefficient, right, and coefficient. So, let us say that is Stanton number is equal to half of the skin friction coefficient, right. Again, for a flat plate, of course, we know, for a flat plate, of course, we know that CF is equal to 0.664 by RE, right. Therefore, for Prandtl, so we know this, right. So, therefore, now Nusselt's number is equal to 0.332, right. If you see here, this expression is Nusselt's number is equal to Reynolds number into half of CF. Okay. So, which is equal to under root RE and Prandtl number to the power 1/3. Okay. Okay. So, this is just to kind of wind this up. I will kind of stop here after that. So, I will just write this. So, now if I were to write this, so half, okay, CF Reynolds number is equal to Nusselt number, okay, into Prandtl number to the power minus 1/3, right. So, this is essentially the modified Reynolds analogy, or well, it's it's named after people, so might as well write them. Okay. So, I think we will kind of stop there. So, I think we kind of did an elongated couple of lessons on using the similarity variable to get solutions, okay, and hopefully this gave you some idea, okay, and how different basically doing a basic math, not too complicated, you should be able to tackle a large number of problems. These are categorized. It's very important to remember that when we are using this, for example, this last one, when we were when we looked at this, right. So, there are conditions here, right. So, when theta is this, right. So, then we wrote this down, and Why is this? That's because, for a flat plate, alpha 3, alpha 2, alpha 4, alpha 3 Prandtl number. So these are things you need to remember, but we get some very interesting results. We start, what we first were doing is trying to get a physical feel for the thing. Now what we did is we kind of did just the math, and from the math now we're trying to get a picture of things, and we see that we're able to kind of go back and forth. Sometimes we start with the math, okay, which seems a little bit complicated, and then it gives you some idea about the actual physical flow. So I think we'll stop here and take up something in the next module. So thanks.